Hello all. So today we are going to discuss the most disturbing topic of DC machine, that is commutation and armature reaction. So for your information, let me first uh, tell you that a few myths that are common, like we have to place the brush at physically means neutral axis, means the brush physical position should be adjacent to the interpolar region, but that is not the true. You do not need to place your physical position of your carbon brush need not to be the interpolar region. Rather, the coil it is going to short, that must be located in the interpolar region, and I am coming to that. Why do we need? But you can see here at this picture that we are having a coil with one side of this coil. This is one side, another side of this coil is here, this dashed because it is in the back side, like you are not able to see it. The front side of the coil is one side of the armature. Suppose it is placed on a means drum shaped object, then obviously you cannot see the other side. Anyway, that is not the business here. What is most important for us at this moment is to understand that coil 1 it is connected with this, right? And what about the other? This 8 is connected with this. You can see that these are the commutator segment 1 and 2, and this brush that is marked with a minus sign, it is going to short this coil. So it is basically short the coil whose two ends are placed at slot 1 and slot 8, and the brush is going to short it. And what is the physical position of this coil? The physical position of this coil is in the interpolar region. Why so? Because we know that if here before we start, we must also consider two different type of EMF. One is statistically induced EMF. Like what happened in case of a transformer due to flux variation. Flux variation or means variation of current. That is also case of flux variation. And another one is dynamically induced EMF. Please check the spelling. I always make some spelling mistake because Word, Microsoft Word, just means damage us in this way that we cannot write a correct spelling by ourselves. So it may so happen that I have made a few spelling mistakes. So please check it. Anyway, so dynamically induced EMF is that it is induced like if what you study in Fleming's right hand rule, that is an example of dynamically induced EMF. So you need a motion for that. It is like you are having a steady magnetic field and your conductor is moving, and therefore the conductor is experiencing a change in flux associated with it. What is the case in case of a statistically induced EMF? In case of a statistically induced EMF, it is the flux that is time vary. And in case of a dynamically induced EMF, the name dynamically comes from the fact that your coil or means conductor across which some EMF is getting induced is in motion. Unlike the transformer coil that are coils that are rest throughout the operation time, here in case of dynamically induced EMF, in case of a DC generator, your coils are in motion. Now, here in these coils, two different type of EMF will be induced. One is that of statistically induced EMF, because whenever you will try to change the current through the coil, there will be some kind of means you are bound to get some means opposite EMF induced across your coil to prevent that change in current. What is the meaning of commutation? Commutation meaning is the change in your current path. Like one current is flowing in one direction, after commutation current will flow in another direction. The English meaning of commutation is the change in path. So if we need to change the current path, then obviously we have to overcome that statistically induced EMF in the volt means coil, across the coil, because after all your coil is an inductive element. Although it is DC, that is why from when we do the steady state analysis we only consider armature resistance, we do not consider armature inductance. However, it is a pure inductive coil with not pure inductive coil, it is an inductive coil, heavily inductive coil with some resistance value present. So you have to consider that. In addition, what is there, that is the dynamically induced. Now, if you means do not commute the coil that are in interpolar region, suppose the two ends of the coil are placed under the polar region and therefore EMF is getting induced across them, and you try to short the coil or to change, then what you will have to work against the dynamically induced EMF. That is also a very dangerous thing. So at least if you try to commute the coil that are at interpolar region, then obviously you are able to only means you have to take care of the statistically induced EMF, not the dynamically induced EMF, right? So how commutation takes place, let me show you exactly by a few pictures. So here in this picture you can understand the means coil. Here you can see that it is coil A is going to experience the commutation procedure. See, coil A is current is flowing through coil A from left to right, left to right, from left side of the coil to right side. Now, when it is first instant, in the second instant, what is happening here? Your brush just short the two end of the coil. Like when your brush position is here, like the brush will be, half of the brush will be in touch with this segment of your commutator, and the half of the brush will be in touch of this segment of the commutator. Like here you can see that the brush is equally placed, like half contact area of the brush is in touch with one teeth of the commutator, another one is with the another teeth of the commutator, and these two teeth are connected with the two ends of your coil A. Like what are the ends of coil A? It is like in the first picture it is where 1 and 8, right? Now when you are seeing this, after this coil, this is the case of commutation, and after this what you will observe that the current in coil A is flowing from right to left. So this is an example of commutation procedure. Now let us understand this in detail. See, suppose we are considering commutation of coil A, and first A and another one coil is connected with one teeth number 1 of commutator, and the teeth number 1 and brush width, here we are assuming that brush width is same as the width of the commutator teeth, right? So brush width, it is totally connected with 1. So whatever current it is collecting from teeth 1, it is the sum of the two coils. One is from coil A, that is carrying IA by A. Another one is from another coil, that is carrying IA by A. Let us consider this IA by A is the total current. So the total current through this commutators, through this brush is 2IA by A. And remember, this 2IA by A has to be constant, because we are expecting a steady current across our through our load circuit. When we will connect, suppose it is a generator case, and when we will connect a load across the brushes, then obviously we expect a flow of a steady DC current through our load. Now here we are also assuming that the current from one teeth to brush is proportional to its contact area. So here you can see that when the brush is slightly in contact with commutator teeth 2 and mostly in touch with commutator 1, the commutator 1 is sharing the like every coil is carrying IA by A except coil capital A. Its current is getting reduced by an amount I1, right? So what is that I1? See, as the commutator teeth 1 is occupying the most of the surface area of this brush, it is sharing the major component of the current, that is 2IA by A minus I1, and this one is sharing the current I1. And how you can validate KCL at teeth 2 of this commutator? Like if I1 is coming here, then IA minus I1 is flowing through coil A, and when you are considering teeth 1, then the total current is 2IA minus I1. So again you are getting the 2IA, that is the steady current. See the beauty here, that is why we call the commutator as a mechanical rectifier. Then once both our brush share the equal amount of coil, means they are equally in touch with the both of the teeth, like 1 and 2. This actually plays a short circuit across coil A, and therefore you are having current flowing from the left and right coil of A, not any but A is not carrying any current. So actually the idea is that means A can carry current, obviously can carry current, but what will happen that if A's two sides are under the polar region, or means experiencing presence of a dynamically induced EMF, then if you try to short A, means try to commute A, commute means what? You are trying to change its current direction. So then the dynamically induced EMF will means oppose your effort towards commutation, right? So that is why we need to be cautious. Now in the next instance, what is happening that teeth 1 is means only teeth 1, the contact area between teeth 1 and the carbon brush is getting reduced, and teeth 2 and carbon brush is getting increased with the motion of your machine or the rotation of your commutator. And what is consequently what we can see here, that I2 amount of current is being collected from teeth 1, and the remaining current is getting the commutator is trying to collect it from teeth 2. Now what is here, that as it can only collect I2 amount of current, the remaining current of this coil should flow through coil A, and that is IA by A minus I2 amount of coil is flowing through A, and here this one. So, or try to understand that previously all in this case it was from left to right, then 0, then here it becomes right to left, and now it is totally right to left. Fine. So this is the case. Now we'll see what is issue with armature reaction. Now people were making comments like armature reaction can make or result in zero speed regulation or whatever. Do remember one thing, that whatever nature, mother nature always wants to maintain balance. We, the people, always try to disturb the nature, but mother nature always try to design or devise the whole ecosystem or everything in such a manner that there is something to balance the energy. Like all this, what is happening here also in armature reaction or whatever you take consider, everything tries to balance the energy. So my idea of engineering is that you try to understand the flow of energy from one path or one part of your system to another part, and then you will be able to figure out everything, like all these harmonics and other complicated tools are there just to make your analysis easier, but your intuition should develop from the basic concept of basic physics, basic concept of the direction of energy flow. We are not doing some abstract mathematics that we will be learning Fourier, Laplace, this, that, and we will then apply these tools without any understanding. Like I was discussing something very interesting with a student, that I do not know how many of you have by this time watched that video of unbalanced operation. You will see, if you watch, that if we ground the neutral, then the phase voltage also remains constant. But at the same time, that can be like an explanation can be provided, like that ground earthing of the neutral provides a path for third harmonic current flow, and that is very interesting. So you must consider all these things, right? So these are the different type of commutation we can see here. The tau c is the is known as the commutation interval or time period for commutation. So typically tau c is very small, because tau c is what? Tau c is the, like you can visualize it, at a very high speed of your machine, say 1500 RPM or something, you need to or 2000 RPM, you need to traverse only a few degree, because your commutator is along the your commutator surface, you just need to traverse a few degree. So it is typically a few, in most of the cases it will be a few millisecond, or in some cases it is smaller than millisecond. So you must be very this current reversal must takes place at a very smooth manner. So what we can see that in case of curve 1, how we can get this type of different curve, that will also be discussed, we will discuss it. Like curve 1 is shown that it is a kind of accelerated commutation, that means the reversal takes place at a very fast speed. Now the curve 2, it is known as like it is somewhat desirable, or it is accelerated but somewhat desirable. Curve 3 is the best one, that is the linear commutation, like smooth transition from plus Ia by A to minus Ia by A. Curve 4 is also known as sinusoidal commutation, that is almost very close to that, means characteristics wise this is very close to your commutation pattern 3, so it is also a satisfactory commutation. The fifth curve that indicate a retarded commutation. So in case of retarded commutation, what happened that, or under commutation we all can also say, the final rate of change of current is very high. So you can see that there is a very high rate of change of current. So it causes a sparking at the trailing edge of the brush. And curve 6 is sharply retarded commutation, that is also an undesirable case. So it causes sparking, heavy sparking across your brush. So we will see that how we will be able to judiciously place like our dynamic EMF and the statistically induced EMF, both this must be 0, so we can get a satisfactory commutation here. So we will use Interpol and means another different arrangement for that. So we will see how to do that. So let us start our analysis. What we see, say this is a separately excited DC motor. Now you can see when there is only current flowing through your field winding, you can find out the direction of the magnetic field by your right hand tip rule. So what you can see that the magnetic neutral plane known as MNA, magnetic neutral plane abbreviated as MNA, coincide with the geometric neutral plane GNA, right? Magnetic and geometric neutral plane coincide with each other. So in that case, speaking that the brushes are going to commute the coil that are in interpolar region. Now when we consider now when we consider our only armature current is carrying coil, suppose you have a DC motor and this is carrying a current coil, so what you will see that your armature, forget about this direction of rotation, your armature your armature, they are producing a magnetic field, and that is in quadrature with your original field produced by your field winding. How can you find out the direction of the armature armature current field? That is, again you have to use the right hand tip rule. If you use, you can find out the direction of current direction of the magnetic field. So basically you are having two magnetic field, they are acting in quadrature. One is the magnetic field produced by your field winding. Obviously you can expect that want to be somewhat stronger, and you are having the means another field that is in quadrature with your field, means your original field, and the intensity of this magnetic field varies with your armature current. So if your armature is carrying full load current, this will produce a stronger armature magnetic field, and if armature is at no load, then that will not produce any magnetic field. So here what you will see that when we will consider this, here you can see that the position of new magnetic neutral plane like the armature, that will try to shift the plane, means armature magnetic field will have a tendency to shift the magnetic plane in the direction of rotation of generator, and in case of motor it will try to rotate opposite to the direction of the motor rotation. Like what was your initial means only field, your magnetic neutral, sorry, not this one. See, your field when armature current was 0, field was having a vector like this. Your field winding can be represented by a vector like this. Now when your, okay, let me draw it here only, then you will be able to understand. See, when you don't have the armature, then you will have a field winding like this. Now when you are having this armature, then what is happening here, either the armature will be in this direction or in this direction, right? Now what we will see that this will cause your means what is the resultant. If this is your field and this is your armature, what is the resultant? You can find out using that parallelogram law. To see, when your field vector was here, then your magnetic neutral axis, that was coincide with your geometric neutral axis, and that is perpendicular to your field winding, and you will decide the coil that is undergoing that will be commutated by your brush should place in this position. However, what we can see, when there is the armature current, depending on the armature current, see this vector is constant magnitude, but this one is variable magnitude. So what will happen? We will have this resultant vector. The orientation and magnitude of the resultant vector will also vary depending on the magnitude of your armature vector, right? So what will be the new position of your magnetic neutral plane? That will be exactly perpendicular to your new resultant vector, like it should be perpendicular with this vector, right? So this explains the whole thing, that this new magnetic neutral plane can be anywhere in between. Like if you consider, like for maximum your maximum armature current, if it's located in this way, and for zero armature current, if it coincide with your geometric neutral axis, Then for other intermediate current, your magnetic neutral plane will be anywhere between in this region, right? It will vary in this region. However, it is difficult for you to know it means in advance, because until unless you load your machine, how can you know? And means even if you know, it is difficult for you to then your machine will be very means rigid. Why it will be rigid? Like if you suppose your machine draw 40 ampere current, and you based on 40 ampere you find out the location of this new magnetic neutral plane, and you placed your brush in such a manner that they will short these two coils, right? So whatever coil, now this is for 40 ampere, right? Now suppose if I want to operate my machine with 15 ampere, there is no harm. But in that case of 15 ampere operation, what you will find, your MNA will be somewhere here. So this is for 15 ampere, but your brushes are here. So obviously you cannot operate your machine at a reduced load, but that is very it is not desirable, means it is an undesirable case, like your machine can only be operated at rated load. Obviously you should not exceed the rated load, that's a different issue, but it is not like that you cannot load your machine with if you put an obligation on you that you have to run your fan at the maximum position of regulator, and you cannot run your fan, and if you try to run your fan at any other position where the fan speed is a bit slower than its maximum position, your fan will be damaged in the long run. Then that is very disadvantageous design, or means it is not at all desirable, because disadvantageous because it will make you total operation operating zone will be very small, right? Only one armature current can be the motor will operate, or motor or generator will operate with only a particular armature current, but it cannot operate with other condition. So you may complain that why I am not drawing all this, because these diagrams will only consume some time, and that is of no good. So instead of drawing the diagram, I just try to share the picture from the book. Now here what you will see, that the total armature electric loading will be how much? Now that we can define it for unit length across our armature periphery, and that will be how much? ZIA divided by pi d. Okay, so here I have not considered parallel path. If it is parallel path, then ZIA, and this one is known as armature electric loading. You will get to know more about this during your design class. So if you want high armature electric loading, then you need to improve the either the conductor materials, or there is not but choices are available there. So what you need to do, you just need to increase the cross section area. Like if you increase the cross section area, then what you will have, you can have a higher value of IA by A. So in that way you can increase the armature electrical loading, right? Now what you can see here, what I just discussed in the previous case, that is same thing you can see here. This is your like these things, this capital A, they are showing the armature field line. This is our you can say that we are taking a means we took a cross section and we are taking the front view of the armature conductors. So what we are like we are means the axis of the armature are parallel to our are perpendicular to our say nose or forehead, and now we are taking the means front view, and then we can see this is the case. Like obviously you are doing a surface development, like your armature was like this, sorry, and you just cut it here, and then you just from that you develop a straight surface. This is known as surface development. You must have read it in your engineering drawing. So this is basically the armature slots, right? And these are the armature conductor. So what we can see that we are assuming that armature conductors are like evenly spaced, and this is the total field produced by the armature conductor. Now what you can see here, first consider these two magnetic field. Here you can see that this is the flux density due to your means armature MMF. Armature MMF is varying in this way, right? And let us first consider the main field. Main field, you will get this kind of trapezoidal waveform. Means if we do some as you discussed that if we make our pole shoes carved and we take serious design means if we design the pole shoes in a very what can I say, in a very ergonomic manner, then what we will have? We will have almost a sinusoidal variation of our field. Otherwise, what would happen? We will get this kind of field. And although this is not relevant, but let me tell you, you can. This is how much? This is 0 to 2 pi, and this is a non-sinusoidal periodic wave. So you can break it like a series of and having half wave symmetry. So this can be explained by means of means first fundamental plus third plus fifth plus seventh order space harmonics, because this angle is totally space angle. So we can express this non-sinusoidal flux space distribution by means of several space harmonics, right? Now this is our main field flux. So what we can understand that the main field flux, although it is non-sinusoidal, but this is our interpolar region, and this one, actually this point and this point, they are the same point, mind it. So if we place our brush here, even the flux distribution is non-sinusoidal, that don't means pose any challenge, because still our brushes are going to short or commute the coils which sides are placed in the means interpolar region. But if you consider the armature MMF, what you will see that this is our armature MMF, and you can easily find out the armature MMF from this. Like if this is the center of the coil, then if you consider the means the value, higher value of x will allow you to consider more number of conductors, and more number of conductors means your n will increase. So if that is the case, then what will happen? We'll have a high number of Ni. So this is the case. Here your Ni was started from negative. Then when you come here at x is equal to 0, it becomes 0, and then when you go, it takes this shape. Now there is another side of this story, that the armature flux, means flux due to armature, will be how to decide. That will be the MMF by reluctance, and obviously the reluctance which will get between these pole shoes, and means not between, rather the under this pole shoe, whatever value of reluctance you will get, your reluctance value will increase when you will move here in the interpolar region, right? Therefore what you will have your flux density due to armature curve is like this. See, these dotted lines are the two edges of your pole shoe, and here your flux density is maximum, and after that even your flux density means MMF is increasing in a linear manner, but you are having a flux density that is getting reduced because your mu in this region, or you can consider it in terms of r is continuously increasing in this region, and again when you are moving here, that like r, if you consider r is like this in this region. Sorry. So whenever you divide it this by this, then you are getting this kind of curve. So this means shaded curve is the flux density, and do remember that we are interested in flux density, not with the MMF, right? So how to find out the resultant? We can do point to point addition, and what we will get, this is our resultant air gap flux or flux density, whatever you say. Now here you see that for this present armature loading or armature current, what you can observe, that instead of the neutral plane being here, the previous neutral plane, which was also in GNA, previously it was GNA, now your MNA shift from your GNA by an angle alpha, right? And this alpha, it depends on the direction of your means in case of generator, it shifts towards the rotation of your generator, and in case of motor, it shifts in opposite direction, right? Now what we want to show you, now see here, we are considering the brush shift beta. So what is the essence of doing that brush shift is to make sure that our like brush actually lies in the magnetic neutral plane, rather than, sorry, not brush lies in the magnetic neutral plane, rather the brush should short or should try to commute the coil that are in the magnetic neutral plane, rather than the coils that are in the geometric neutral plane. So what we have done, we have just shifted the brush by an angle beta. So after shifting beta, what we can see here, that this is the depending on the brush shift, we can have our MMA produced by the brush, and accordingly we can have our waveforms. So waveforms, we can see the resultant waveform. Now see the resultant waveform. Here the position of the brush, it is at magnetic neutral plane. Geometric neutral plane is indicated by that where your field flux reversal takes place, but your resultant flux reversal takes place at the new position of your brush. So it is somewhat this correct decision, but the problem is that to know the brush at an advance means before you go to load your machine, how can you know that what would be the value of the current that you need to supply, or like this? That is an issue with that brush shift approach. Now here what we can write, that the demagnetizing armature mmf per pole, if we write it like ATD, then that is like half into the why 2 beta we are considering. Just let me show you another picture, then you will be able to understand. See, once you shift your coil, then within this span, this 2 beta, whatever is your coil, that half of the coil is actually producing a field that is exactly in opposition to your main field, right? Main field, if we consider that main field is from this is the direction of main field from left to right. Now see here, it is like in this zone, these are the cross. So cross means what? Cross means current is means flowing towards your this surface of this paper, or means it is going in to your conductor. So if you apply the right hand tip rule, you will find that these conductors that is in the span of these 2 beta, they are producing a field line like this. So that is exactly in opposition with your main field flux. So total this ATD per pole should be, as there is 2 poles, should be half into armature conductors mmf in that zone. So you will find this is like ATD these remain constant. Now what is the portion of the conductor that is placed in this region? That is 2 beta by 2 pi. So that will be how much? Right. Now what we can see, that the remaining portion like here you can see that in that area that is 2 pi minus 4b, what you are getting, these conductors, they are producing field that is exactly in quadrature with your main field. Like if your main field is from north to south in this way, your these conductors are producing field in this way, right? So this is why they call as cross magnetic field. So what is the amount of cross magnetic field is that we are talking about one pole, right? Like per pole we are trying to calculate. Oh God. So that is will result you. So in case of multipolar machine also we can show that this same thing holds good. Like as we are calculating the formula for flux means demagnetizing and cross magnetizing per pole, we will be able to see that the same thing holds good. Right here you can see that this is the demagnetizing armature turn per pair of poles. So you are getting it here, and like for means the remaining area will be for the your cross magnetizing MME, right? So now let us check it with some pros and cons of this. So in order to means we realize that brush shift can be done to avoid the commutation problem, but the lack of flexibility with the brush shift, like it is only amount of shift is totally dependent on the load current, and for a particular amount of load current you need to shift your brush particular amount, and that is not a feasible solution. Your machine housing is you cannot even think of providing such feature in your machine that you will be able to change the brush and shift angle, because that will make your machine structure structure wise it will become vulnerable to your external disturbances and other things. So that is why brush shift is no way a feasible solution. So in order to provide a feasible solution, what you need to do is to think about something that can produce the same effect but without doing that kind of brush shift. So what we do, we introduce a concept that is known as interpol. So what is the purpose of introducing this interpol? These interpoles are placed at interpolar region, and they try to reduce that kind of demagnetizing MMF of the armature, and accordingly you realize there is no such shift of your magnetic neutral plane. Magnetic neutral plane still coincide with your geometric neutral plane. So what is the means how to design the interpole? As we know, in case of a generator, the armature current exhibits a tendency to shift your this is your normal location of your this is GNA, this is also MNA for IA is equal to 0. Now when you will load your motor, then what will happen? Or load your generator, what will happen? For generator, it will try to shift the MNA towards your if this is G is the direction of rotation of the generator, then it will try to shift it in this way, right? So in that case, what you need to do, so how you can make sure that this cannot means what we can consider like this loading of armature is trying to extend the effect of this north pole instead of means the effect of north pole and shear, it tries to take it here also. So what we need to ensure that even if you load the armature, the MNA should remain same for IA is equal to some value of current. So that is why what we can do is that in case of generator, we should wound the interpole in such a manner that it provides the polarity of the leading pole tip, right? Why? Because it has, in case of a generator, try to understand that armature reaction has a tendency to extend the magnetic field of the your means trailing pole tip. Like after it means in case of generator, if we draw it, even if we means exceed its if we consider that this region, the upper half of this red line should be dominated by north pole. But when you load your generator, what we see that it tries to means extend this region from here to here. So what we can do, if we place an interpole that is having the polarity of this one, then it will do what? It will neutralize the excess amount of your means armature MMF that tries to bend your or tries to deviate your MNA from GNA, and make sure your MNA still, even if you load the machine, still coincide with your GNA. However, one thing it is we must make it very clear that the shift of your load or shift of your magnetic neutral plane depends on what? Your armature current. Field current remains constant. So if armature current, if you want to control that armature current, then what do you need to consider? That this interpole must be connected in series with the armature. This is point 1. What is second point? That like in case of what I was trying to say, of the leading poles case of motor have the polarity of trailing poles. Right. What is the third point? That as your interpole, it is supposed to produce a variable magnetic field or variable MMF. What you want that therefore what you want, the reluctance in the flux path of interpole magnetic field must be sufficiently high to avoid the chance of magnetic saturation. Like if your flux path gets saturated, then what will happen? Your armature will produce sufficient demagnetizing MMF, but your interpole could not combat it because its flux will be limited by the means saturation curve of your magnetic material. So that is why it is not desirable, and it should means equally counterbalance the armature MMF irrespective of armature loading. That is why we consider it. But there is another means when you are, this is the beauty of engineering, when you try to strengthen or enhance one or means try to focus on a particular aspect, you will means every time you will see that some other aspects or other performance will be affected. What I am trying to say, if you are thinking about increasing reluctance path, reluctance in the interpole path, typically how can you do that? By maintaining a large air gap. Like here, you can see that main pole shoes are curved, but interpole shoes are straight to enhance the reluctance in the path. But that will do what? It will, in other way, it will produce chance of huge leakage reactance, and that leakage reactance is no way desirable. Why? And also that interpole, whenever you will introduce interpole, think about the armature current. This armature current, it is means although the interpole, they are, which current they are getting. First of all, think about the interpole, whether they are getting the alternating current or the direct current. Obviously they are getting the direct current, because there is no point of feeding your interpole with the armature alternating current. But in case you want to reverse your motor speed or something, then in addition to armature means inductance voltage or something, you need to counterbalance that. Here when you introduce the interpole, you have to counterbalance that also. So in order to, means you have to be very calculative. Means although this is the design issue, and you will be get to know more about it in your coming means not coming, in your next to next semester, when there will be a dedicated course on the sectional class on electrical machine design. Professor Gopalakrishna generally takes that class. So you will get to know more about this, but you have to think that, oh, okay, not like we want to increase the leakage means reluctance of the path, and in that way, what we the way we such we means in such a manner we placed interpole in a way that makes the reversal of the machine extremely difficult. You should not do that, right? So here is a picture where we can see these are the main poles and these are the interpole. Obviously these two are same interpole, right? Don't get confused that there is 2 pole and 3 interpole, not like that. This is 1 north pole interpole, this is 2 south, means these 2 are actually the same south interpole. Now what we know that in case of a generator, it should be the leading pole tips, like if you consider generator. So what you can see here, that we are not doing the brush shift, but due to this interpole, here this is the flux due to main pole, then we are getting unfortunately here the armature flux they have not drawn. Let me draw it, or at least try to draw it. Like how we know the armature flux, like here if you have the armature waveforms, then what you will get it like, okay, flux due to armature current they have shown. Yeah, this is a flux due to armature current. So what is happening here, you can see that this flux due to armature current due to the placement of this interpole. Previously what was happening here, that flux was like this. Right, and that caused the shift of magnetic neutral plane from geometric neutral plane by an angle beta. But due to, so here you can see the armature flux due to armature current, and what you will observe here, that this flux due to armature current, that is shown here. Now one thing you must understand, that here what they are shown by this dashed line, it is the corresponding effect of flux due to armature current and interpole. Had we considered only flux, then what would be the nature of that flux? That would be something like what we have seen in the previous cases. Just let me draw that one. You will get an armature MMF like this. From one Previously, this was our armature MMF, right? And what about the armature flux? What we were getting previously? We were having an armature flux like this blue line shows armature flux without interpole. So when we introduce interpole, what we can see that here it is clear, it is drawn here in this dash line in this picture. You can see that here they are means coinciding at that means when you are at interpolar axis, then their residual flux becomes very small. Why there is a small means flux still exists? Do you think it is unusual or it is a design practice? I would like to hear from you, like why there is a little flux, why not? It starts from 0. Here also we can have it like 0. So instead of means this modified curve we are getting due to the introduction of this interpole. So why we are introducing that interpole? Why we are using this form of wave shape? Why not we use our interpole to exactly means make sure that resultant flux waveform value becomes 0 at interpolar region. So we have to understand that, and I would like to hear it from your end. Now little mathematics, like if you consider, just let me check. If you consider here after introduction of interpole, you can see that there doesn't exist any means demagnetizing MMF. So the total MMF can be considered as the cross magnetizing MMF. So armature cross magnetizing ampere turn per pole is what that in the previous case what we observed in that before introduction of interpole, yes, this was the armature compensating armature cross magnetizing loading for armature. However, here what we can see that after introduction of our interpole, the total flux has become cross magnetizing, and what we can write that interpole flux, that is ATI, or better to say that like ATI will be how much interpole flux? That will be ATA or ATC what is this LIG? This is the air gap length LIG. So this is the ampere turn required per pole to create the interpolar or interpole flux through air gap of length Lig, right? So what is that? What we know that ATA is how much? ATA is what is this ATLIG? That is beta C by mu naught. This mu naught is 4 pi into 10 to the power minus 7 into LIG into KIG. What is this LIG and KIG? This LIG is the gap length and KIG is the gap factor, right? So, sorry. Now, this is for Interpol. When we will do some numerical problem, you will be able to understand it more clearly. However, do understand one thing, that the Interpol MMF is effective only in commutating zone, right? Means interpoles are present where? In the interpolar region, and they can only ensure a smooth commutation. However, the armature reaction effects are overcome only under the interpoles and your resultant flux. If we see this waveform once again, you will see that here the effect of flux under pole, like this interpole, it's okay, but what about under the normal pole? That is still distorted. Now that if a DC machine, the idea behind introduction of interpole instead of brush shift is to make sure that your machine should be flexible, and can serve different load. Maybe may able to, what can I say? May able to like supply or meet a load demand for different value of electrical or mechanical load. Now, in case of a DC machine that is subjected to heavy overload, or it's working with a weak magnetic field, like either when you are below base speed and means your torque requirement is very high, and otherwise you are working in a region where your means you are doing the flux weakening control above base speed. So what is the essence of this mentioning these two phase? The essence is that below base speed, although your flux remains constant, but for your heavy load, your armature current will be very high. Either for electrical load or for mechanical load, your armature current will be excessively high, and that will cause a considerable effect of armature means produce a considerable amount of MMA, armature MMA, and therefore it will cause a considerable or tangible deviation from your nominal field flux. Nominal field flux distribution, your machine loading will cause a tangible deviation from your nominal field flux. Or else when you are doing that flux weakening control, what will happen? Here instead of this, what you will get? You will get means this kind of trapezoidal cut, but height of that trapezoid will be somewhat means if this is say in this scale, if this is let me just draw for flux weakening control what type of curve you will get. You will get it like this. Now means make sure you understand one thing properly, that the armature conductor never experience separately the field winding or the armature movement. They always experience the resultant flux. So if the resultant flux means if your field winding, either field flux is weak or your armature flux is too strong, in both the cases it results in considerable distortion in your flux pattern. So how we can overcome this? Even if you introduce Interpol, they can only combat the, or means not combat, rather they can only take care of your flux waveform or flux shape waveform near interpolar region, but not under the direct pole shoes. Now what will happen, like any coil whose two coil sides are under the influence of this peak flux will have a large dynamically induced EMF in it. If this rotational voltage exceeds the permissible limit, the air between the adjacent commutator segments will cause some kind of sparking. Like see, I am trying to say it like, if you have, say here you are having coil 1, or say here you are having coil 1 and 8. So this is the amount of flux experienced by the side of coil 1. One side is coil, this is one coil. Now the two end of the coil is connected with a commutator segment. Now another coil that is that are in this region, it will means it may so happen the coil is connected with adjacent brush. Now what will happen, you will see that there is means considerable voltage difference will be means you will find a considerable means difference between the dynamically induced EMF in the two sides, like one that is experiencing this peak flux, another somewhat experiencing some other values. So this is very dangerous. Try to understand what I am trying to say. Let me get back to the previous picture. Yes, suppose here this one, it is experiencing positive maximum flux, and these 8, although they are okay, let us select some other like this 5. Okay, so this 5, it is experiencing plus 5 or connected with plus 5, and what is the another terminal of, yeah, here this is experiencing minus 5. So what voltage you will get here, it is a very high dynamic voltage will be induced across this coil with side 5 and 12. Now, if you consider the adjacent, these coils are connected where? With commutator segment 4, and this 5 is with between 3. So, what will happen that although they are not in interpolar region, but the voltage induced between these will be very high and may cause, this is see, these are the commutator teeth, but this interteeth is you have placed some mica or some kind of insulator material in the interteeth region, or means between two adjacent segments of commutator you always place some insulator. So what you can have a spark takes place from here due to breakdown of the local layer, or what you can have, suppose you are having this here and another coil is here, so due to considerable voltage difference an arc may takes place between these two also, but there is the means chance of means arcing takes place is very high between these segment 3 and 4, right? Now the issue here is that, like, how can we handle this? Obviously, introducing interpolar cannot means Interpol can only take care of Interpol can make sure these 1 and 8 they are associated with a very small amount of flux, so that can be ensured by the Interpol, not about the 5 and 12, right? So what we should do, like, we will consider another arrangement that is known as compensating winding. So how we can place the compensating winding? The best way, because this kind of traveling is caused by the, or means we can realize this kind of distorted flux when we are under our main poles. So it is best, means the best possible solution to this problem is to place your like compensating winding exactly here in this pole shoe region, right? So all these are placed here, and another thing what we do is like the Interpol, should produce a proportional effect to counterbalance the demagnetizing effect of armature. Like the compensating winding should also produce a proportional effect to the armature current. It should not, means otherwise it cannot neutralize the distortion of flux. So like Interpol, it must be connected in series with your machine, right? And it should be like the polarity of this should be in such that if here it is it should carry the current, compensating winding should carry the current just opposite to your armature conductor. So So what would happen, try to understand that if this armature conductor, what type of flux will be produced by this armature conductor, you can find it out by using right hand tip rule. They will try to produce a flux in this way, right? And what about them? They will, this compensating winding, they will try to produce a flux in this direction. So what would happen, that these two will cancel out each other, and you will have a kind of, means these two will cancel out each other. So what you will have here, you will have only your pole flux that is working in this direction present in your machine. Earlier what was happening, when your compensating winding was not there, this black curve was not there. Due to this, what was happening, these red curves were getting in this way. Right. So now when you introduce this, they are doing or producing a perfectly balancing action of the armature conductor under your main poles, and therefore there is a perfect flux distribution, and we will get something like this type of flux distribution. When there is compensating winding, compensating MMF, you can see that it is exactly same, and means opposite of armature MMF, and therefore it is just neutralizing, and you are getting the resultant flux waveform in this shape. So one question may comes in your mind, that if compensating winding can do this, do we really even after introduction of compensating winding, do we need interpole winding? Think about it. I would like to hear the answer from your end, that why do we need it? So we can also express the mathematics for, or write the mathematics for compensating winding. Compensating winding should be how much? Here 80 is the armature MMF per pole, so that will be how much? And from this we can simplify it like right. So let us consider a few problems, then that will also clear your understanding. Okay, so here is the first problem. A 4-pole generator supplies a current of 140 ampere. It has 492 armature conductors. Two configurations we have to consider. One is wave connected, another one is slab connected. When delivering full load, the brushes are given an actual lead of 10 degree. We know what happened in case of a generator. What happened? In case of a generator, the armature current or armature movement exhibits a tendency to shift the MNA in the direction of generator rotation. Like it tries to shift or give an angular deflection of means your magnetic neutral axis from geometric neutral axis in the direction of armature or your generator rotation. So that is what they want to mean by the term lead. Calculate the demagnetizing armature ampere turns per pole. The field winding is separately excited and takes 10 ampere. Find the number of extra field turns necessary to neutralize this demagnetization. Also calculate the cross magnetizing armature ampere turns per pole. So first, wave connected. So for wave connected, you have to find out the demagnetizing armature ampere turn. What is that? That is ATD is equal to what? Means beta Z IA by 360A, where A is the number of parallel path where your wave and lap does matter. Similarly, ATC will be how much? That is for cross magnetizing field will be now beta is in mechanical degrees. So number of total conductor, everything is given. Z is equal to 492, IA is equal to how much? 140, A is equal to 2. So demagnetizing ampere turn ATD is equal to how much? 10 into 492 into 140 by 360 into 2 is equal to 956.6780. I am copying from a book. Please verify it by your own. There may be some calculation mistake. Now the field winding is separately excited. Find out the number of extra field turns. So it is implied that field current remains constant to that 10 ampere. So what is the extra number of field turns? Okay. Now fraction number of turns is not possible, so you can consider 96 turns. Now what is ATC? ATC will be 1 by P minus beta by 180 into Z by A. So 1 by P is 1 by 4 minus 10 by 180 by Z into A. Z is 492, sorry, IA into 140 by 2. So that will give us 3348.33 ampere turn. Similarly, you can do it for lap. What changes you have to consider for lap? For lap, all these will be, this A will become 4. So if A will become 4, then what would happen here? It will become half of the previous value, 478.33. So that will be 478. So it will become, now what would happen here? Similarly, you have to change it to by 4. So what you will get here, half of the previous value, so 1674 point. Okay. Now let us consider the next problem. Basically, this is not very interesting. What you will find interesting when we will start considering something for this means demagnetization and cross magnetization for AC machine. That is extremely interesting. So a 6-pole 40 kilowatt 400 volt wave connected DC generator has 492 conductors on the armature. The brush are shifted by an angle of 8 mechanical degrees to obtain sparkless commutation. When delivering full load current, calculate the demagnetizing and cross magnetizing. So first what you can do is to find out the current, that is full load current. Wave collected, so number of parallel path A is equal to 2, Z is equal to 492, IA, FL we already get. Now beta is equal to 8. So same formula ATD, that is 8 into 492 into 100 divided by 360 into 2, that is 546.67 ampere turn per pole. Now cross magnetizing will be how much? Cross magnetizing ATC is equal to 1 upon P minus beta by 180 into ZIA by 2A. So what is the total number of poles? 6 poles. So 1 by 6 minus 8 by 180 into 492 into 100 into 2 divided by 2 into 2. So it will give you 1503.33 ampere turn per pole. Actually, these numericals are not very intriguing, just straightforward application of formulas. If you know the formula, you can solve the numericals. A 4-pole lap-wound DC generator has 60 slots. Okay. There are 8 conductors per slot and per flux per pole is 0.05 Weber. Calculate the speed required for a generated EMF of 440 volt. Also find the demagnetizing and cross magnetizing ampere turn per pole when the load current is 30 ampere if the brushes are shifted by an angle of 8 degree. Okay, fine. So generated EMF. So what is the total number of conductor? 60 into 8, 480. What is E? E is equal to P phi j n by 60 into P by A. So here it is 0.05 into Z480 into Acha. E is given, N is not given. So it is 440. T into N into how much? P is 4 by 4 into 60. So if you do side transposition, you will get N is equal to 1100 RPM. Very high value. Okay. Now brush shift angle beta is equal to here they have said 8 electrical degree, so we have to consider it in mechanical degree, so that means 2 by P into 8, so 2 by 4 into 8, that is 4. So what is ATD is equal to beta Z IA by 360 A P. Here they have mentioned ampere turn per pole. So where is the calculation? Yes, there was a mistake in the book. So beta Z IA by 360 A. So A hit into 4 into 480 into 30 into divided by 360 into 4. So what you will get here? 40 ampere turn per pole. Now what will be? Just let me check whether recording is. Cross magnetizing ATC is equal to 1 upon P minus beta by 180 into J into IC into 2 by A. 1 by 4 minus 4 by 180 into 480 into 100. Oh no, here it is 330. 230 into 2 into 4. What we are getting, it is like here it means answer is also incorrect. What is 4 and 180? This is 360. 90 So basically 82 into 5, 410 ampere turn per pole. What is the next problem? 4 pole 40 kilowatt 250 volt lap shunt generator has 400 armature conductors. Brush are given a lead of 5 commutator segments. Okay, calculate. This is our just simple means like there is no such change in understanding. Like if you have 400 commutator, then you can always understand the angle between two adjacent commutator segment, that is 360 by 400. Okay, so what is your brush shift effect, mechanical brush shift effect? So that is equal to some value you will get. Okay, just a minute. So port pole has 400 armature conductor. Okay, so one twist is there. 400 armature conductors. It is commutator segment, so not in terms of conductor. So 400 armature conductors means, if we consider simple coil, then there are like 200 coils and you need 200 armature segments. Sorry, not armature segments, commutator segments. Let me show you. Yes, here you can see what is the total number of conductors present, that is 24. Started with 1 and total 24. So 1 to 24, 24 conductors are here. How many you have, how many commutator segment? Only 12. So whatever number of conductors you will have, your commutator segment will be just exactly half of that, right? So yeah. 200 commutator segments, right? So 200 commutator segments, therefore what is the brush shift angle? Beta is equal to five into 360 by 200, that is 9 degree. So what is full load current? Similar to the previous problem, we have to find out the full load current, that is 4 this is our load current, right? Do note that here we are considering the 40 kilowatt as output. So what about shunt field current? So that is equal to, what is shunt field resistance? 50 ohm. So 250 by 50 is equal to 5 ampere. What is total IAFL? IAFL is equal to 160 plus 5, that is 165. So total, what is total? Okay, what we need to do? We have to find out extra shunt field turns per pole to neutralize the demagnetization at full load. What is full load demagnetizing mmf per pole? That is ATD is equal to 9 into 400 into 165 divided by 360 into 4 is equal to, as per their calculation, 412.5 ampere turn per pole. So extra shunt field turns. Now, extra shunt field turn per pole will be how much? 412.5 by 5. What is 5? That is shunt field current. So that is equal to 83 turns extra is required, right? Now let us consider another problem. Four pole 80 kilowatt 250 volt lap connected DC machine has 256 conductors. Find the number of turns required on each interpole. If interpole air gap is 1.2 centimeter and the interpolar flux density is 0.3 Weber per meter square, neglect the effect of leakage. And also, so what we need to do, first of all, you have to find out the full load current, that is so this is 320. Now number of armature conductor is how much? 256. A is equal to how much? 4. LIG interpolar air gap is 1.2 into 10 to the power minus 2. Now interpolar flux density is equal to 0.3 Weber per meter square. Gap factor we have to assume 1 if nothing is specified. So what is that? Is equal to how much? ZIA by 2AP plus BC mu naught LIG KIG. So 256 into 320 by 2 into 4 into 4 plus 0.3 into 12 into 10 to the power minus 3 by 4 pi into 10 to the power minus 7 into 1. So that results in 5424.8 ampere turn, right? So IANI is equal to this much, 5424.8 ampere turn. Now what we know that interpoles are connected in series, so they are also carrying the same current, 320 ampere. So number of turns required for interpole is right. Now here for 14 pole 2000 kilowatt for 40 volt DC motor as a lap wound armature with 1100 conductors. The ratio of pole arc to pole pitch is 0.68. Calculate the number of pole face conductors of the compensating winding in each pole required to obtain a uniform air gap flux density under the pole faces. So basically here we are talking about the cross magnetizing field and the compensating winding. So what you need to do, first of all you need to find out the current IA, that is how much, 2000 into 10 to the power 3 by 440 4545.45 ampere. Now number of parallel path A is equal to 14. So that compensating winding is how to do that. It is pole pitch by pole arc, pole arc by pole pitch. So pole arc by pole pitch is equal to how much? That ratio is given, it is 0.68 into 1100 Z into 4545.545. This is I divided by 2 into 14 2AP. What happened? So basically you will get, it is like 8673.5 ampere turn per pole. So that is equal to compensator winding conductors per pole will be how much? See, this is ampere turn. Now how many conductors do you need to form a turn? That is 2 conductors, and we have to divide it by the current to get the turns, and then if we double it, then we will get the required number of conductors. As per the book calculation, it is coming around 4 conductors per pole. Now let us take another example. A compensated DC machine has 1800 means 18,000 ampere turn per pole. The ratio of polar to pole pitch is 0.7, interpolar flux density and air gap length are 0.25 Weber per meter square and 1.0 centimeter respectively. For rated armature current of 800 ampere, compute the compensating winding conductors per pole and number of turns on each interpole. So compensating winding will be how much? Same like previous problem, ATW is equal to 0.7, that is the .7 into 1800, so that is 12,600 ampere turn per pole. So compensating winding conductors per pole will be how much? 12,600 divided by 800 into 2, because compensating winding is also connected in series, so that they will also carry 800. The total will be 32 as per the book calculation. Please verify those calculations by yourself. Now ampere turn of the interpole winding will be, please note this formula. See, this actually gives us what? This gives us H, that is ampere turn per meter. Now, if you multiply with this Lij, that is the unit of length, you will get ampere turn, right? So, and this is the amount of resultant flux produced by ampere turn and compensating winding. So this will be 18000 minus 12600 plus 0.25 by 4 pi into 10 to the power minus 7 into 10 to the power minus 2. Again we are considering gap factor is equal to 1. So we will get 7389.4 ampere turn per pole. Now if you divide it by the current, that is 800, you will get actually it will come more close to 9, means if you normally approximate it, you should settle down with 9, but here we should take 10 because the interpole, there is no harm if interpole flux is slightly higher than the required amount, but if interpole flux is means interpole ampere turn is less than the required amount, then that may cause a serious commutation problem, right? Now let us consider the another problem. The compensated generator means already compensating winding and interpoles are there. 10,000 armature pole arc ratio, pole arc pole pitch 0.7, the length of interpole air gap 1. So it is just like the previous one. So I hope you can do this by yourself. The answer is like ATW is equal to 0.7 into that ATI. As per their calculation, it is 5546.48 ampere turn per pole. So you can do it. Now let us consider another problem. Okay, now a singleton coil has in the commutating zone an inductance of 0.025 millihenry. Find what commutating field is required for the straight line commutation of 25 ampere. So EMF induced will be how much? We are considering magnitude only. So you will find that DI is equal to 50 ampere. 25 ampere means here it is plus 25 to minus 25 ampere. It looks like that. What happened? Yeah. So let us consider the commutation time is delta t second. So L is equal to how much? 0.025 millihenry. So for how much E you will get here? E will be right. So for linear commutation, what you need to do, that dynamically induced EMF in the commutating coil must counterbalance this value. So you need dynamically induced EMF in the commutating coil. That is how much it will be. The magnitude will be 2 VAV This is for a single turn coil. If for multi-turn, you have to consider it N. For single turn, it is two side, that is why 2. So here, if this armature conductor moves a linear distance delta x in delta t second, then we can define V like delta x by delta t, right? So what we can write that BAV L delta x is equal to, now see, this is what? This actually gives us the actual means flux, and if delta x is the width of the commutating region, means then means like how to get delta x, that is d by 2, or d is the armature dia by 2 or machine dia by 2 into the angular span of the commutating region, that will give you delta x. So that is equal to so what you can write that 2 by this flux, if this is phi c, by delta t is equal to point that LDITT so commutating region flux need to be 0.625 milliweber as per their calculation. Please check it. Right.